Okay, students, in this video we will be talking about this return ratio analysis, but before talk about this analysis, I have to just tell you the reason uh, behind what analysis we have followed for this feedback analysis or feedback methods. So in general, the most common approach that are used for a negative feedback circuit analysis, or one is the two port analysis, and this is the analysis that we have been using uh, during the discussion of this feedback network. And the second most widely used method is known as return ratio analysis, or in short I would call it as RRA, which is nothing but the acronym for this return ratio analysis. Now in the first case, let me talk about how are these two analyses are different from each other, and why there is a move from the first analysis, which is the TPA analysis, to the return ratio analysis. So why there is a need for us to move from one analysis to a different type of analysis. Okay, so first let me talk about the differences. So the two port analysis in general is used for a feedback network which is considered to be an unilateral feedback, whereas this is a return ratio analysis is used for bilateral feedback. So in the case of a unilateral feedback, the signal actually travels only in one direction, okay, whereas in the case of a bilateral feedback network, the signal may travel in both the directions. Okay, so this is the subtle difference between these two analyses, but let me try to emphasize about the flaws that we would end up having when we use this TPA, that is having considering all this feedback network along with the basic amplifier propagating the signals only in one direction. Let us try to talk about the flaws that we have when we encounter or when we use this TPA analysis. Okay, and later to rectify those flaws, we just use this return ratio analysis, and later we'll use this analysis to compute what is known as a loop gain expression. Okay, yeah. So let me try to bring back the circuit that we have used for this feedback network. So we know that there is a signal Xs, and X could be a current or a voltage, okay, and that will be generally mixed up with a feedback signal which is labeled as Xf, and the input to this basic amplifier or the open loop amplifier in general is taken as small letter a with an arrow at the top indicating the direction of flow of the signal. Okay, so from Xi to X naught, and this is the type of signal that it generates out of this basic amplifier. Okay, and we assume that this basic amplifier is unidirectional. There is no signal transition from X naught to Xi, so this has not been considered. Okay, and that's the reason why we say that the two port analysis is basically unilateral. So we always assume that the signal flows from Xi to X naught, and even in the case of a feedback, we were using this beta with an arrow pointing from right to the left, where the signal input is fed from X naught and a partial or a fraction of the signal is being fed back as Xf. Okay, so even here this feedback network is considered to be an unilateral, means that the signal always moves from X naught to Xf, and there is no signal transition from Xf to X naught. Okay, so that is how we assumed during the analysis of two port analysis. Okay. Now let us take a simple example rather than having this block diagram. Let me just show a simple case where when we try to use this beta network or the feedback network, which is being purely built by making use of this passive feedback network, uh, the assumption of a signal travel from X naught to Xf, like the only direction in which the signal flows, or assuming that the feedback network is always a unidirectional, may not be an ideal case. Okay, so in practice the signal can also move from Xf to X naught. Okay, so that is what we would try to address it. Okay. So let me just bring back, yeah. So let me just try to build a simple example why this won't be a practical situation for a feedback network to be assumed as a kind of unidirectional network. Okay, so I'm just going to build a type of amplifier where there can be a considerable amount of input impedance and the voltage drop across this input impedance of this basic amplifier is considered as Vi, and there will be some sort of voltage controlled voltage source with a gain of A times that of Vi, and there will be some sort of output impedance Z naught, and that is being fed back here. And let us go for a non-inverting amplifier configuration where the signal Vs is being applied at the input with some sort of Zs, and there is a feedback network that connects the output to the input. And yeah, so this is something like it looks something like a kind of voltage amplifier. Okay, yeah. So clearly you could be able to see that there is a kind of forward amplifier or the forward basic amplifier which is modeled as a kind of voltage controlled voltage source, and there is also a feedback network uh, which is being built by making use of this ZF as well as ZS. Okay, so the most important fact about this circuit is that uh, this composition of ZF and ZS is basically a bilateral transmission circuit. Okay, so there is something like the signal can flow from Vs or basically from Vi to this V naught, and also there is a possibility of current flow or current flow basically from V naught to Vi. So depending on the potential difference between the Vi and V naught, there are two ways by which the signal can flow through this impedance ZF. Okay, and so basically what we have is a kind of feedback network that seems to be a symmetric bilateral transmission. Okay, yeah. So and even in this case one could also assume that this forward basic amplifier, even though we can model it as a kind of bidirectional, still most of the basically since the value of this V naught is way larger than the value of Vi, we always assume that the backward transmission is quite small. Okay, so one could neglect that, and one could even assume that this basic amplifier is basically a unilateral circuit or a unilateral network. Okay, but whereas this feedback network in general will be a bilateral circuit or a bilateral network. Okay, and due to which there will be a signal flow in both the directions. It is not a kind of, it cannot be modeled as a kind of unilateral. So now having this bilateral transmission through this ZF and ZS uh, basically causes some sort of inconvenience in applying this formula in calculating uh, the closed loop gain, which is written as AF, which is V naught by Vs, and could be written as small letter a, which is nothing but the gain of the basic amplifier divided by 1 plus a beta. Okay, so again this 1 plus a beta is nothing but the amount of feedback, and in this one could see that the beta is not a kind of unilateral circuit, but rather it's a kind of a bilateral transmitting circuit through this feedback network. Okay, and due to this bilateral transmission through this feedback impedance, it makes the finding of this basic amplifier gain A and the finding of this beta or the finding of the feedback network beta becomes difficult using the analysis that we have discussed earlier. That is the two port analysis method. One cannot use this two port analysis method to evaluate these values. Okay, so that is what it becomes more difficult for us to evaluate such two terms out of this two port or out of this TPA analysis method. Okay, now so this basically demands an alternative analysis for the computation of few things. One of them is the feedback gain, okay, and the other one is the loop gain. So we need an alternate method to compute the closed loop gain, the loop gain, and even the input and output impedances of output impedance of closed loop amplifiers. So we need an alternative analysis, and actually there exists an alternative analysis which is often called as return ratio analysis, and this analysis in general uh, is is often easier than this two port analysis. Okay, so than this two port analysis, uh, and also uh, you might wonder the inclusion of this computation of this loop gain. So why is this loop gain is so important in evaluating this or in the evaluation process of any feedback network is that uh, for stability it is only this loop gain that we will be using in order to compute the stability of any closed loop negative feedback circuit. So even the computation of this loop gain is far more important than the other parameters like the closed loop as well as the input output impedance of a closed loop amplifier. Okay, so in a way I am just trying to emphasize that this loop gain is one of the most predominant quantity that one has to analyze quickly based on the feedback network that I have, and provided the feedback network is a kind of bi-circuit, or sorry, what is the name, yeah, bilateral transmission. Okay, so whenever this feedback network is a bilateral transmitting circuit, then the evaluation of all these quantities has to be much more precise, and basically we want this loop gain to be evaluated more precisely than the normal way where we found this A and beta using this TPA, where the both this A as well as beta were considered to be a unilateral circuit. Okay, so the computation of this in turn would impact the stability of our circuit. Okay, so we want a precise quantity to be evaluated for these loop gains in short, and we will be using this method, return ratio analysis, to evaluate this loop gain. Okay, so hope that you are clear with what I am trying to say. So the next thing is that in short, yeah, so the next thing is that this return ratio analysis, okay, is generally used to compute the transfer function of the loop gain. Okay, so so I'll be using this discussion of this return ratio analysis by making use of this loop gain, or with the computation of this loop gain calculation. Okay, now I will also write on the formula of this loop gain. So I generally use this notation of capital T to represent the loop gain formula, and generally, since because the open loop gain is a function of frequency, even this loop gain will also be a function of frequency, even though we consider beta to be a kind of frequency independent parameter. And later one could use this result of this return ratio analysis along with what is known as something known as Blackman's formula. Okay, so one can use the result of this return ratio analysis So in general, the return ratio analysis will give us this particular factor, and one can combine those results into this Blackman's formula to calculate all this closed loop input as well as the output impedances. Okay, so probably you might feel that this RRA method is quite tedious just because we are applying those results in a completely new different ways to compute those things. But in short, the usage of this Blackman's formula, we will not cover up these things in our course, but what I'm trying to say is that I'll just tell you a kind of essence out of this Blackman's formula is that in the computation, or while we try to compute those closed loop impedances, input output impedances in while using this TPA analysis, what we did is that we first try to compute the open loop input impedance as well as the output impedance, and later what we did is that we use this amount of feedback, and we just try to multiply or divide these impedances values based on the type of connection that we had. If it is a series, what we did is that we just use this amount of feedback to multiply onto the impedance, and then we got the impedance value as the closed loop impedance value. Or if the connection was a shunt, we just divided the impedance value by this quantity of amount of feedback, which is 1 plus a beta, and then we found and we got the value of the impedance for the closed loop amplifier. Okay, so it involves a lot of identification of the type of feedback network that we are using, and then later applying appropriately these amount of feedback onto it. But whereas in the case of this Blackman formula, which is basically used to compute the closed loop input and output impedance, one need no need to consider any type of connection that it makes. So it is something like a kind of unique formula that is applied in general to all type of amplifiers, all different 4 type of amplifiers that we have discussed. Okay, so in a way, this method is quite easier in order to calculate these input and output impedance, and it's also the calculated input and output impedances are more precise, will end up having a more precise result than compared to the method that we have used in the TPA analysis method. Okay, so in the case when you want to evaluate the more precise values of the input and output impedance, it is always the go for answer is a Blackman's formula. But since because it is not part of our syllabus, we will not discuss upon these things, but I would urge you to follow this textbook, which is titled as Analysis and Design of Analog Integrated Circuits. Okay, so this is the title of the textbook. So wherein a part of the discussion I have taken from this particular textbook, and if you want to get more in depth in order to know how to calculate this closed loop input and output impedance using this Blackman's formula, one could use those method. Okay, one could follow this particular textbook. Okay, and here I'll be talking about only a part of the discussion that is being handled in this particular textbook, which is the computation of the loop gain. But using this RR method, one can not only compute this loop gain, but one can also compute the closed loop amplifier gain as well as the closed loop input output impedances. Okay, yeah. So those are the basic theory that I just want to discuss today. So let us try to get into the work. So basically, this RRA method works something like this. Okay, so let me write the title, which is nothing but the return ratio analysis method. Basically works like this. So let us consider back our feedback network that we have before, the simple block diagram. We just copy here. So, note here in this case, the assumption of this beta network being a unidirectional has been um, relaxed. So, it can have bidirectional. So, I am just going to remove that beta with arrow mark, but while the other part, that is our basic amplifier, can still be considered, need not to be mandatory, but still one could use this unidirectional principle for the basic amplifier. Okay. So, this let us consider as unilateral circuit itself. Okay. Just because the assumption that we have is this value of the signal x naught is always much larger than the value of xi, and due to which we one could approximate this basic amplifier just to have a unilateral signal flow. Okay. But whereas the other end, where this beta network is basically constructed by using this passive circuits, we can consider this to be a bilateral circuit. Okay. So, in this whole analysis, we will consider this as to be a bilateral circuit. Okay. So, now this RRA method depends on incorporating two important modifications to the circuit. Okay. So, the two modifications that one has to incorporate onto this feedback network is that the first one is to kill the input source or the independent source. Now, in the case of an input signal source, which is a current, you can kill it by open circuiting it. If it is a voltage source, you can kill it by short circuiting the source to the ground. Okay. And the second modification that one has to do is to break the circuit. Okay. So, probably this is something that we have to work out a bit. So, break the feedback loop of the circuit. So, what I try to mean here is that, let me just try to bring out the copy of the circuit that I have done. Let me try to demonstrate what has been written at the top onto the circuit. Okay. So, killing this input source is by making this signal Xs to go to 0. Okay. So, there is no signal through this, and if this Xs is a current source, then you can kill it by open circuiting it. If it is a voltage source, you can kill it by short circuiting it. Okay. Yeah. So, this is what you have to do for the first step, and the second step is to break this feedback loop. Okay. So, the way sometimes most people will do is to break the output. Yeah. So, it is something like breaking this particular network connection that I have towards the input of this beta network, and then later to this feedback network input, we will try to apply an input signal which is known as xt, and xt is nothing but the test signal, and in turn, where this particular feedback is being broken out, the signal output is taken as xr. So, basically the xr or x naught is same, and it generally works like this. So, let me write this output of this feedback network signal xf as, or in terms of xt, as beta times that of xt, and let me write the input signal to this basic amplifier xi as the summation of xs and xf. Okay. So, due to which I could write it as xs minus xf, right. And since because we made this x s is equal to 0, the output of this xi, or basically the input of xi, can be written as minus beta times that of xt, and the xr, which is nothing but the return signal, okay, or x naught, is returned as minus a beta times that of xt, and it follows that the loop gain given by the negative, yeah. So, let me write this. So, in this case, the loop gain can be returned as something like a beta, and that is nothing but it is returned as a negative ratio of the returned signal to the applied signal xt. Okay. And it should also be obvious that this applies regardless of where we exactly broke the circuit. Okay. So it need not to be broken only at this particular juncture, but uh, we can break the circuit loop, the basically the loop containing the beta as well as the A network at any point. Okay. But however, in breaking this feedback loop of a practical amplifier, one has to ensure that the condition, let me write this, one has to ensure that the conditions that existed prior to breaking the loop does not change. Okay. So probably this might be some sort of confusion that you might have. Okay. So uh, so basically we are talking about the second point, and what we did is that we just try to break the circuit randomly at a connection between this input and output of the between the input of the basic sorry, between the input of the feedback network to the output of the basic amplifier. Okay. But it need not to be always like we have to make this break only at these 2 points. Okay. But what one has to ensure is that you can break at any point, provided the conditions that existed prior to breaking the loop should not change. Okay. So in general, this can be achieved, or this, whatever the condition that we are talking, can be achieved by terminating the loop where it is opened uh, with an impedance equal to the to that seen before the loop was broken. Okay. So let me just try to explain this. Okay. So hope that you are clear with this statement. So right now we need to find an impedance. Okay. And that impedance uh, has to be measured before the loop was broken, and we have to substitute that impedance where exactly the loop was opened. Okay. So graphically, let me try to show this with respect to a voltage amplifier feedback loop. Okay. So I will just take two circles here. Let me just choose the shape. Okay. And let me use one more. Yeah. So let us assume that whatever we have here is a, just a second. Yeah. Yeah. So let us consider that whatever the loop that I have drawn with two circles is a kind of voltage feedback loop. Okay, so let us assume, okay, and let us assume that we are breaking this particular loop at a particular node which is marked as x prime, and whatever the impedance that I have seen through this break, let us mark that impedance as zt. Okay. Now what we do is that while breaking the loop, after breaking the loop, I have to ensure that the circuit conditions has to be same even after breaking the loop. So what it really means is that, say for example, I am breaking the loop at exactly x prime, then I have to ensure that the loop is terminated with the same impedance that was seen before. Okay, so I have to have an impedance zt to be substituted at the place where it is opened, and while the other end of the loop is being applied with some sort of input uh, source. Okay, and that input source, since because I am assumed that this particular loop is basically a voltage feedback loop. Okay, the type of source that I am connecting at the input or towards the left side of the open uh, feedback loop is considered to be as Vt. Okay. Now clearly what happens is that this signal Vt would then travel through this different network along this particular path, and then it appears across the Zt as a kind of voltage drop which is marked as Vr. Okay, and the ratio of this Vt or Vr divided by Vt would give us the value of this uh, 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 the value of this loop gain, which is A beta. Okay, and it always have to have this negative sign just because of the feedback that we had was a kind of negative feedback. Okay, so the ratio of Vr or the negative ratio of this Vr by Vt will give us this loop gain. Okay, this is what we theoretically want to know. Now, right now you might have a question in your mind like how to identify this input impedance or basically the impedance Zt, and so that impedance could be used to terminate the loop to mimic the exact circuit conditions that existed before breaking the loop. Okay, so this is a kind of worry that you might have, but wait, uh, we don't need to worry too much, since because we are dealing with active elements like MOSFET in the basic amplifier. Okay, so in this case, so since there are active elements that are involved in this basic amplifier, one could model this basic amplifier as something like a kind of voltage controlled voltage source. These are known as dependent sources. So usually we'll be using this dependent sources to model this basic amplifier, right? So say for example, we were using this voltage controlled voltage source for the basic amplifier when we try to model uh, the basic amplifier as a kind of voltage amplifier. Hope that you remember. So say for example, it takes in an input voltage of Vi and then converts into a gain times that of Vi, right? And even if the circuit has some sort of non-linearities like Ri and some sort of output impedance like R naught. Okay, so even with these things, we still have this dependent source, which is in this case this particular guy. Okay, so this is known as the dependent source of the basic amplifier. And even in the case, let us take the other example where we have used a voltage controlled current source to model what is known as a transconductance amplifier. So which looks something like this. Again, we have an input voltage which is measured as Vi, and even if we consider this non-ideality, we will have this resistance Ri, and we would be having some sort of dependent source, which in general would be a current source, and if we consider the non-ideal condition of the circuit, then I could include an R naught across the output port. Okay, so what I'm trying to say is that there is some sort of dependent source that exists in this basic amplifier, and one would exploit this dependent um, source as a kind of breaking point to evaluate this return ratio formula, or basically this ratio of xr divided by xt can be used over there. Okay, so we no need to worry about the computation of this zt as shown here, and then use that zt to terminate the loop and then apply this vt. So we no need to do such all this huge thing, but rather we'll just follow a different step. And uh, and basically, as I said, uh, this return ratio formula depends on those dependent sources. Okay, so let me write it as return ratio analysis, and this return ratio analysis basically depends on, or the procedure to follow using this return ratio is that um, first thing is to kill. So as usual, we have to kill the input source, and after killing this input source, the next thing that we have to do is to disconnect, or is to break the circuit. Okay, now where exactly this breaking has to do is by this particular method that I'm going to write, that is uh, the dependent source that we have in the basic amplifier are basically disconnected from the rest of the feedback circuit. So this disconnection uh, gently mimics or or basically introduces uh, a kind of breaking in this feedback loop. Okay, so which introduces a break in the feedback loop. Okay, the next thing is, after breaking, or after disconnecting this dependent source which mimics the break in this feedback loop, the next thing is that on the side of the break, so it's a rather huge statement. Let me complete this statement. That is not connected to the dependent source. Okay, so we are choosing the side where exactly the dependent source was being disconnected. To that side, we have to apply, or basically connect, an independent source. Okay, so we are removing a dependent source and we are applying an independent test source signal, which I labeled as xt. And the type of signal that I have to apply, either it's a voltage signal or a current signal, depends um, on the type of dependent source that we had before. Okay, so it has to follow the same sign and the type as the dependent source. Okay, so in case if this particular statement is confusing, what I'm trying to say is that um, when we try to remove this dependent source in the circuit, I have to replace, in this case I have a voltage dependent voltage source, and this voltage dependent voltage source has to be replaced with a signal which is Vt, okay, which is again a voltage. So whereas in this case, where we have a voltage controlled current source, we will be replacing this dependent current source with a signal which is It. Okay, so and also the current direction is supposed to follow the same direction. Okay, so if it is flowing from top to bottom, even the It which has been introduced here should also follow the same current direction. And however, we had labeled here as plus and minus, even the Vt also has to be placed with plus and minus with the same signs. Okay, and that is what we really mean by this particular third statement. Okay, now once we connect this independent source xt in the place of the dependent source, the next thing is to compute the or find the return signal XR, which is generated by the dependent source. Okay. So this particular signal is generated by the dependent source. Okay. So we let me show this with a kind of example. Until otherwise I could demonstrate, you might feel a bit of confusion here, but I will just try to remove this ambiguities out of your mind while doing some problems. Okay. So now so once we have done with this calculation of this return signal, I could use this return ratio formula, which is R, which is defined as XR by XT, uh, and this gives me the expression for this loop gain. Okay. Yeah. So now, without further ado, let us quickly jump onto a problem, so that whatever we have learned, we will just utilize it here. Now let me consider. So I will be doing some two exercise problems here to demonstrate how to compute the loop gain using this return ratio analysis, and using those 4 steps that I have listed here. Let us try to demonstrate this process. Okay. And this is just for the computation of the loop gain. I am not going to show how to evaluate the closed loop gain, nor I am not going to show you how to calculate the closed loop input output impedances. Okay. So if you want, you can just go through the textbook that I have listed to know more about it. But as of now, for the syllabus point of view, we do not have those topics, so I will skip those kind of discussions, but rather I will just go with this return ratio analysis method alone. Okay. So let us assume that we have some sort of voltage source with a resistance Rs, and it also has some sort of feedback RF, and that has been fed to a basic amplifier or an op amp. So we, as said before, whenever there is an op amp, we will just assume that this op amp is always a voltage amplifier. So inside this op amp, let me model that there exists a kind of input impedance. Let me model this input impedance as Ri, and the voltage drop across this Ri is taken as Vi, and that has been utilized as a kind of voltage controlled voltage source over here, and it also has some sort of finite output impedance, which is modeled as R naught, and let me write the gain here, which is minus AV times that of Vi. So what it really means is that we are talking about a negative feedback circuit. Okay. So with a negative sign here and a plus sign here, and bring out this and put it to the ground. Okay. Yeah. So hope that this circuit is quite familiar with what we have discussed, and let me connect it here, and we connect this RF to the output, which is a V naught. Okay. Yeah. So now onto the circuit. For the very first thing is we need to figure out the dependent source. Okay. So in this case, we have a dependent source which is nothing but the AV times that of Vi, right. So let me mark this particular location where this dependent source has to be disconnected from. Okay. So let me redraw the same picture. So hope that you have copied this picture that I have drawn, and right now the next picture will show you the disconnection, as well as since because the input source is a voltage source, I have to kill this input source by short circuiting this particular voltage source. So what it really means is that we have a circuit condition where we have this Rs, and then we had this resistance Ri, and the drop across this, let me put this Ri towards the left side, and the drop across this Ri is measured as Vi, and that was being fed to a voltage controlled voltage source. But this circuit or this dependent source has to be disconnected from the rest of the circuit, right. So So means that there is no connection after this. And the last statement also had stated that this voltage AV or minus AV times that of VI can be read as a return signal. The fourth statement that was being stated here said that we have to find the return signal generated by the dependent source. So whatever the signal that we are getting out of these two nodes is being measured as the VR signal or the returned signal. Just because it's a voltage controlled voltage source, we are measuring this output of this dependent source as a VR. Okay, and in the place where we had this voltage controlled dependent source has to be replaced with what is known as an independent source. Okay, so let me model this independent source as Vt with the same polarities. Okay, and that's been applied to the rest of the circuit. So we had a resistance R naught, and then we had a feedback from the output V naught to the input side. Okay, or basically to the Vi. Yeah. So this is the entire circuit setup that we have, and now that we need to find out the ratio of Vt or VR by Vt. Okay. So now what I am going to do is that let me just try to label few things. Uh, First, let us try to calculate the value of this Vi. Okay. Now, one could see that let me just try to figure out this Vt. You could see that this has been connected through this resistive path. Okay, and this is one of the component that I have, and there is also one more component where this Vi is not only a drop across this resistance Ri, but it is also a parallel combination of Ri and Vi. Okay, so one could use a simple voltage division rule in order to compute the voltage drop of Vi. Okay, so let me write this Vi as the drop across the parallel combination of Rs and Ri divided by the summation of both these impedances. It's a simple voltage division rule, nothing fancy here. Rf plus R naught, just because these two impedances were in series, we have just added up, and that has been multiplied with the potential of Vt. Okay, and also one could write the value of this Vr is nothing but it's the product of the gain, which is Av times that of Vi. So in the place of Vi, one could substitute this expression so that the ratio, the return ratio, which is minus Vr by Vt, can be returned into Av. Okay, yeah. So this is the formula that we have found for this A beta. Okay, so this return ratio or the ratio of Vr by Vt will give us this loop gain formula. Okay, so let me just move on to the next one where we will try to have a different circuit setup. And let me have a current In, and there is a feedback connecting between the input and output, which is labeled as Rf as before, and we have a V naught here. Okay, yeah. So now one has to redraw the same circuit with the kind of MOS transistor being replaced with a voltage controlled current source, right? So let me just try to do that. So this is the second level of circuit, and we are trying to draw the small signal model of the circuit that has been drawn before. Okay, yeah. So we have this resistance Rg, and one could use this voltage drop across this Rg as Vgs, right. And inside this mass transistor we have a voltage controlled current source, and we know that it depends on the polarity of this Vgs, the current flow, and based on this polarity we have a current which is Gm times that of Vgs, and there is a finite amount of output impedance which is R naught between the drain and the source, and later what we have is this Rd resistor, and we have this V naught, and we also have a feedback resistance that connects the input to the output as RF. Yeah. So once we draw the small signal model for this given circuit, the next thing is to figure out the existence of a dependent source. Okay. So now here in this case, the dependent source that we have here is this voltage controlled current source, and so let me mark this points so that this dependent source has to be disconnected from the rest of the circuit, and then over this particular regime we need to apply a current source. Okay. So let me try to complete all those things, and let me also try to show you how to measure the signal IR out of the circuit. Okay. So the previous case we had a different kind of circuit setup, and right now we are dealing with a completely different set of circuit setup here. Okay. Yeah. So according to the first rule, we have to kill this input independent source. So killing this current source is nothing but it's open circuiting it, right. So let me open circuit this, and what is left over is just the resistance Rg. Okay. And still the drop across this Rg is always read as Vgs, and we had this dependent source. Now this dependent source is a current source, and we know that this current always loops. Okay. And we want to extract a current which is basically so the current that is measured will give us the value of this IR. Okay. And the direction has to be in the same direction. So what it really means is that this current flow has to flow in this loop, and whatever the current that is looping here is measured as the return signal IR. Okay. Now for this disconnected point we have to apply an input signal, right. So in this case the input signal has to have the same direction in which the GMVGS was flowing. So I have just followed the same flow, and then this was being connected to the rest of the circuit where we had the resistance R naught and the resistance Rd, and there was a feedback resistor that gets connected between the sorry, between the input and the output. Okay. Yeah. So now let us try to evaluate the output voltage V naught. Okay. And let me mark this current that we have as IT. Okay. So now let us try to evaluate this impedance or this output node potential V naught here. Now basically since because we are pumping in a current and we have a bunch of resistance here, one could easily calculate this output impedance V naught, right. So but one has to be careful in evaluating this. Okay. Now one could see that this impedance R naught and Rd not only is connected between this node V naught to this ground, but there is also one more branch of resistance that also gets connected. So what it really means is that it is not just R naught Rd that are in parallel, but also this Rf plus Rg also appears in parallel to it, and the current flow of this IT has to flow across all those three parallel resistors in order to evaluate the parameter of V naught. Okay. So let me just try to write the expression for V naught, which is the current, and this current is flowing in opposite direction, right. So I have to write it as minus IT here, and that is flowing across this parallel combination of R naught, Rd, and this Rg and Rf, which are in series. Okay. Yeah. So this gives us the value of this V naught. Now one has to evaluate the value of this VGS, right. So again one could use this combination of this RF and RG to evaluate the value of VGS in terms of V naught. Okay. So, again one could use this basic voltage division rule, which is VGS can be returned in terms of V naught as the drop across RG divided by the summation of RG and RF. Okay. So, it is a quite simple formula, and now that we need to evaluate this component of IR. So, this IR is returned as something like GM times that of VGS, and now that we need to substitute all of these quantities over here, so that we will have this GM and RG plus RF into this entire quantity. Okay. So, now let us try to combine few things such that we can use this formulation. So, let us consider that this quantity that I have bracketed here is one of the like say for example, it is RA, and the RG plus RF is RB. So, when we have two resistors that are in parallel, we know that it can be written as RA into RB divided by RA plus RB. So, let me write this this parenthesis this expression inside this braces as something of this form, so that there will be some few common terms that one could use to cancel out. Okay. So, we have this quantity multiplied with R naught in parallel with RD, and at the bottom we have this RG plus RF plus this R naught in parallel with RD. Okay. So, as you could see that there is one of the common term that one can use to cancel from both the sides, and finally what we have, yeah, I forgot this symbol, the multiplication of quantity of minus IT. Okay. Yeah. So, finally the return ratio, which is nothing but minus IR, it is always a negative ratio of IR by IT, which is equal to GM RG and then R naught RD divided by RG RF plus R naught RD. Okay. Yeah. So, I hope that this return ratio is nothing but this A beta term, or the quantity of this A beta. Okay. So, we have done with these two problems, and let me try to complete the session today. So, I just want to read out some summaries here. Okay. So, the return ratio analysis is basically an alternate analysis uh, for the feedback circuit analysis, and it does not use this two port analysis method. Okay. So, when we use this two port analysis method, the very difficult task for us is to identify the type of connection that we have at the input as well as the output of the basic amplifier, or the, yeah, around this basic amplifier, and then one has to involve in the computation of this closed loop amplifier input and output impedance with the involvement of multiplying or dividing the those quantities, or basically the open loop output impedances and output like input impedances quantities by either by multiplying or dividing those quantities by the amount of feedback in order to evaluate the closed loop input and output impedances. So, that was rather a kind of tedious work. Okay. We have to think about this beta network in terms of two port networks model, and then a lot of computations and thought process has to be put in. Whereas in this method where we use this return ratio analysis, no such thought process is being used. The only thing is that figure out a dependent source, replace that dependent source with a independent source, and then try to apply the signal xt and measure the return signal XR, and then that gives you the A beta term. Okay. So, it is a quite easiest process which never involved the type of connection that it makes at the input and output, and it is a quite simple process. Okay. So, so right now I will just close this session. Thanks for watching. We will have the discussion in WebEx. Thank you.